Picture this somewhere in the depths of space. An explosion tears through the cosmic darkness. In just a few seconds, it unleashes more energy than our Sun will produce over its entire 10 billion-year lifetime. This isn't science fiction, it's a gamma-ray burst, one of the universe's most violent and mysterious events. These cosmic beacons, born from collapsing stars or colliding neutron stars, flash across the universe like fleeting fireworks, but their brilliance outshines entire galaxies. And the most distant ones, they're time travelers carrying whispers from the universe's infancy, from eras so ancient that Earth didn't even exist yet. What makes gamma-ray bursts so fascinating isn't just their raw power, but the stories they tell. Each burst is a cosmic detective story, a clue to understanding how the universe evolved, how stars lived and died in those early, chaotic chapters. Some of these bursts come from so far away that their light has been journeying toward us for nearly the entire age of the universe itself, over 13 billion years. That means when we detect them, we're not just observing an explosion, we're peering back in time, witnessing moments when the cosmos was still in its fiery, formative youth. Over the next few minutes, we're diving into 30 astonishing facts about these distant gamma-ray bursts, phenomena so extreme they stretch the limits of our imagination. We'll explore how they form, why they're so bright they can be seen across billions of light years, and what secrets they unlock about the early universe. From mind-bending energies to cosmic cataclysms that rewrite the rules of physics, this journey will take us to the very edges of what we know, so buckle up because what lies ahead isn't just science. It's a voyage into the deepest, most violent, and awe-inspiring corners of existence. Gamma-ray bursts explode across the cosmos like celestial flashbulbs, blindingly bright, vanishing just as quickly as they appear. In a span shorter than a coffee break, these bursts unleash more energy than our Sun will emit in its entire lifetime, flooding the universe with gamma rays, the most powerful form of light. Their brevity makes them elusive, but their brilliance ensures they're impossible to ignore, even halfway across the observable universe. The story of their discovery reads like a Cold War thriller. Back in the 1960s, American satellites designed to monitor nuclear tests instead picked up mysterious flashes of gamma radiation, not from Earth but from deep space. Scientists were baffled. Were these signals from secret Soviet experiments, extraterrestrial messages? It took decades of detective work to realize these bursts weren't man-made or even local. They were coming from billions of light years away, born in the deaths of massive stars or the collisions of ultra-dense stellar corpses. What makes these cosmic fireworks so valuable to astronomers isn't just their violence, it's their role as time machines. Because light takes time to travel, the farther away we detect a burst, the further back in time we're looking. The most distant gamma-ray bursts act like cosmic postcards, carrying snapshots of the universe when it was just a fraction of its current age. Their extreme brightness cuts through the fog of billions of years, letting us study an era when galaxies were still taking shape and the first stars were transforming the darkness into light. In a way, every distant burst is a message in a bottle, a remnant of a universe we otherwise could never see. Imagine a cosmic explosion so ancient that when its light began traveling toward Earth, the universe was just a toddler, only 630 million years old. That's GRB 090423, the most distant gamma-ray burst ever detected. This record holder erupted a staggering 13 billion years ago when the first galaxies were still clumping together and the universe hadn't even reached 5% of its current age. Its light spent more than 90% of cosmic history racing across the void before telescopes finally caught its dying glow in 2009. Scientists pinpointed its mind-bending distance using a phenomenon called redshift, the stretching of light waves as the universe expands. GRB 090423's light was stretched so dramatically that its redshift measured 8.2, meaning its wavelength had expanded by over 800% by the time they reached us. To put that in perspective, most galaxies we study have redshifts below 1. This extreme redshift isn't just a distance marker, it's a time stamp confirming the burst as a relic from the epoch of reionization, when the first stars and galaxies were burning away the cosmic fog of hydrogen gas that filled the early universe. What makes this burst so extraordinary isn't just its age, but what it tells us about that chaotic era. GRB 090423's existence proves that massive stars once capable of collapsing into gamma-ray bursts were already forming and dying violently when the universe was barely 6% of its current age. These early stars weren't like the ones we see today. They were giants hundreds of times more massive than our Sun, burning ferociously and dying young in titanic explosions that seeded the cosmos with the first heavy elements. Detecting this burst was like finding a fossil from the universe's first generation of stars. Its afterglow, faint but detectable in infrared light, carried chemical fingerprints revealing a primordial environment almost devoid of elements like carbon or oxygen, just hydrogen and helium, the raw materials forged in the Big Bang. This snapshot confirms theories about the so-called Dark Ages, the murky period before starlight filled the cosmos. Each photon from GRB 090423 is a messenger from an era we can't observe any other way, a time when the universe was taking its first steps from darkness into light. The discovery reshaped our understanding of cosmic dawn. Before GRB 090423, some models suggested the first stars formed later or in isolation. But this burst sheer power, and the fact we detected it implies that massive star formation was already widespread, lighting up pockets of the early universe with brilliant, short-lived flares. It's a reminder that even in its infancy, the universe was anything but quiet. It was a fireworks show of collapsing stars, searing radiation, and cataclysms whose echoes still reach us today. While newer telescopes may someday spot even older bursts, GRB 090423 remains a benchmark. It's proof that gamma-ray bursts aren't just local oddities, they're universal phenomena, lighting up the cosmos from its earliest chapters to the present day. And with each distant burst we find, we're not just adding to a catalogue of cosmic explosions. We're piecing together the story of how a dark, empty universe became the star-filled tapestry we see tonight. Gamma-ray bursts aren't just cosmic explosions, they're portals to the past, offering glimpses into a universe we can no longer see. When astronomers detect a burst from 12 or 13 billion light-years away, they're effectively looking back to a time when galaxies were newborns and the cosmos was a turbulent sea of raw hydrogen and helium. These distant flashes act like scientific time capsules, preserving details about the environment they traveled through on their epic journey to Earth. What makes them so invaluable is their afterglow, the fading light that lingers for hours or days after the initial explosion. As this light passes through ancient gas clouds and early galactic structures, it gets imprinted with chemical fingerprints. Atoms in these primordial clouds absorb specific wavelengths of light, leaving dark lines in the burst spectrum like barcodes. By decoding these absorption lines, scientists can determine what elements were present in the universe's first billion years and in what quantities. One groundbreaking discovery came from GRB 080319, a burst whose afterglow revealed clouds almost entirely devoid of heavy elements. Unlike modern interstellar gas, which is laced with carbon, oxygen, and iron, these ancient pockets contained little more than hydrogen and helium, the pristine remnants of the Big Bang. This confirmed that the very first stars hadn't yet polluted their surroundings with the heavier elements forged in their cores, but it's not just about chemistry. The afterglows also illuminate the structure of the early cosmos. Some bursts pass through multiple gas clouds on their way to us, each at a different distance. Like a cosmic ultrasound, these layered absorption features map the universe's skeleton during its infancy, showing how matter clumped together before galaxies fully formed. One burst's afterglow even revealed a vast filament of gas, a thread of the cosmic web that would one day collapse into a supercluster of galaxies. Perhaps the most startling insight comes from how these bursts interact with the universe's early fog. For hundreds of millions of years after the Big Bang, space was filled with neutral hydrogen that absorbed ultraviolet light, making it opaque. But as the first stars and galaxies ignited, their radiation ionized this gas, clearing the fog in a process called reionization. Distant gamma-ray bursts help pinpoint when this happened. Their ultraviolet light gets partially absorbed if they're emitted before reionization ends, giving astronomers a way to track how and when the universe became transparent. The detective work doesn't stop there. By studying the host galaxies of these ancient bursts, or rather, their faint shadows, scientists have found that many originated in small, chaotic dwarf galaxies, not the majestic spirals we see today. These galactic toddlers were likely still merging, their gravity pulling in streams of gas to fuel furious bursts of star formation. The fact that they produced gamma-ray bursts suggests they contained massive, unstable stars, celestial giants that lived fast, died young, and seeded the cosmos with the first heavy elements. Every distant gamma-ray burst is a Rosetta Stone for the early universe. Their light carries encrypted messages about the birth of galaxies, the death of the first stars, and the slow clearing of the cosmic haze. Without them, we'd be blind to the universe's most formative eras, forced to guess at conditions we can no longer directly observe. But thanks to these far-flung beacons, we're not just reconstructing cosmic history. We're watching it unfold in real time, one brilliant flash at a time. When a star many times more massive than our Sun reaches the end of its life, it doesn't fade quietly. It goes out with a cataclysm so violent it can briefly outshine an entire galaxy. This is the cosmic birthplace of long-duration gamma-ray bursts, explosions lasting more than 2 seconds and often stretching to several minutes. Unlike their shorter cousins born from neutron star collisions, these marathon bursts trace back to the deaths of supermassive stars in events called supernovas on steroids, packing 100 times more energy than a typical stellar explosion. At the heart of this spectacle lies the collapsar model, a process so extreme it pushes the limits of physics. As a massive star runs out of nuclear fuel, its core, no longer supported by outward pressure, implodes under its own gravity. In mere seconds, this collapsing core crosses a point of no return, warping space-time so severely that it forms a newborn black hole. But here's where things get wild. Not all the star's material gets swallowed immediately. Some of it swirls around the black hole in a frenzied, superheated disk spinning at nearly the speed of light. This cosmic blender generates twin jets of particles and radiation, focused into narrow beams by magnetic fields stronger than anything we can produce on Earth. The jets punch through the dying star's outer layers at over 99.9% the speed of light, heating the surrounding gas to billions of degrees. When these relativistic jets finally break free into space, they produce the gamma-ray pulse we observe, a beacon so intense it cuts across cosmic distances. The physics behind this is mind-bending. The jets aren't just fast, they're structured like cosmic lasers with internal shock waves that amplify their energy. As different layers of the jet catch up and collide, they create gamma-ray flashes like celestial strobe lights. Meanwhile, the rest of the star isn't going quietly either. The outer layers rebound from the collapsed core in a titanic shockwave, triggering the hypernova explosion that often accompanies these bursts. What makes long-duration GRBs so special is their connection to star formation. Because only the most massive stars, those 30 times heavier than our Sun or more, can produce collapsars, these bursts act like cosmic signposts for regions where stellar giants are being born and dying. When we detect a long GRB, we're not just seeing a black hole's birth, we're witnessing the violent end of a star that likely shaped its galactic neighborhood, seeding space with heavy elements essential for planets and life. Observations back this up. The host galaxies of long GRBs tend to be active star factories, rich in gas and dust where massive stars form frequently. And the bursts themselves often show chemical signatures of freshly forged elements like nickel and iron, debris from the exploded star's final moments. It's a reminder that destruction and creation in the cosmos are two sides of the same coin. The same explosion that snuffs out a star also sows the seeds for future solar systems. While short GRBs might steal headlines with their compact violence, long-duration bursts offer something equally profound, a direct link to the life cycles of the universe's most massive stars. They're cosmic storytellers, revealing how the deaths of these giants shape the evolution of galaxies across billions of years. Every time one flares in the distant universe, it's not just an explosion we're seeing. It's the dramatic final act of a star whose brief, brilliant life helped build the cosmos we know today. While long gamma-ray bursts announce the deaths of massive stars, their shorter cousins' flashes lasting less than 2 seconds tell an entirely different cosmic story. These brief but insanely energetic eruptions come from one of the most violent mergers in the universe, two neutron stars slamming together at nearly the speed of light. Imagine a pair of city-sized objects, each so dense that a teaspoon of their material weighs 1 billion tons, locked in a deadly dance that ends in a cataclysmic embrace. When they finally collide, the impact is so violent it ripples the fabric of space-time itself. The landmark event GW170817 changed everything. Detected in August 2017, it was the first time astronomers caught both gravitational waves and gamma rays from the same cosmic smash-up. As the Laser Interferometer Gravitational Wave Observatory, or LIGO, picked up the spacetime trembles, NASA, a Fermi satellite, simultaneously spotted a short gamma ray burst just 1.7 seconds later. This 1-2 punch confirmed what theorists had long suspected: neutron-star collisions are the engines behind short GRBs, but the real magic happens in the aftermath. The collision spews out a swirling, superheated debris cloud laced with neutrons, a cosmic crucible where atoms get shredded and reassembled in extreme conditions. Under this neutron bombardment, ordinary nuclei rapidly gobble up extra neutrons, then decay into heavier elements through a process called rapid neutron capture, or the R process. In mere seconds, this alchemy forges staggering amounts of gold, platinum, and other precious metals, enough to seed entire galaxies with solid gold planets. Follow-up observations of GW170817's afterglow revealed something even more astonishing. Over days, the merged object's glow shifted from blue to red, a telltale sign of heavy element production. Spectroscopy confirmed the presence of strontium, gold, and other R process elements totaling over 10 times Earth's mass. This single event likely created more gold than exists in our entire solar system, proof that your wedding ring's atoms were forged in a similar cataclysm billions of years ago. These collisions don't just make bling, they're cosmic recycling plants. Neutron stars are essentially the compressed cores of dead stars, packed with leftover heavy elements from previous generations. When they merge, they release this stored material back into space, mixing it with fresh R process elements to enrich future stars and planets. Without these violent reunions, the universe would lack the diversity of elements needed for rocky planets or life itself. Short GRBs are more than just brilliant flashes. They're the universe's way of marking where the heaviest elements are being minted and scattered across the cosmos. Every time we detect one, we're witnessing the birth of materials that might one day end up in someone's smartphone, spacecraft, or even their DNA. It's a humbling reminder that the stuff we're made of didn't come from peaceful processes. It was forged in some of the most extreme violence the universe can muster. On October 9, 2022, the cosmos turned up the brightness to 11. A gamma-ray burst designated GRB 221009 erupted with such ferocity that scientists are still puzzling over the data. Nicknamed the BOT brightest of all time, this explosion unleashed more energy in 10 seconds than our Sun will emit over its entire 10 billion-year lifespan. Even more astonishing, this wasn't some distant, ancient burst. At just under 2 billion light-years away, it was practically in our cosmic backyard compared to typical GRBs. The numbers defy comprehension. Sensors on NASA's Swift satellite were momentarily overwhelmed, their automatic shutdown systems kicking in to prevent damage like a camera blinking after a lightning strike. The burst's initial pulse carried photons with energies exceeding 18 tera-electronvolts, making them some of the highest energy gamma rays ever recorded from such an event. To put that in perspective, that's about 10 trillion times more energetic than visible light. If you could somehow convert that energy into mass, each photon would weigh more than 30,000 hydrogen atoms. What made the BOT especially bizarre wasn't just its raw power, it was its lingering afterglow. Most gamma-ray bursts fade quickly, but this one kept shining brightly in X-rays for weeks, like a flare refusing to burn out. The usual explanations didn't quite fit. Typically, a burst's afterglow comes from shock waves as the jet plows into surrounding gas, but the BOT's persistence suggested something more complex, perhaps a central engine that kept running far longer than models predicted, or an unusually dense environment around the progenitor star that fueled prolonged emission. Theories abound about what could have spawned such a monster. One leading idea points to a magneto-rotational hypernova, a hypothetical scenario where an extremely massive star collapses with both a powerful magnetic field and rapid rotation. This double whammy could have funneled the explosion's energy into exceptionally narrow jets, making them appear brighter when one happened to point directly at Earth. Others speculate the star might have been a rare WO-type Wolf-Rayet star, a helium-rich, pre-supernova oddball already shedding material at furious speeds before its final collapse. What's undeniable is the BOT's scientific impact. As the closest extremely luminous GRB ever recorded, it offered an unprecedented close-up of these phenomena. Its light carried detailed information about the structure of its relativistic jets, the chemistry of its host galaxy, and even the density of the intergalactic medium it traversed, data that would have been too faint to decipher in more distant bursts. Perhaps most intriguing is what it implies about GRB frequency. Statistically, a burst this bright and relatively nearby should occur only once every 10,000 years. Yet we caught one within decades of having telescopes capable of spotting it. Either we're incredibly lucky, or our models need adjusting. Maybe the universe cooks up these ultra-bright events more often than we thought. For astronomers, the BOT wasn't just a record breaker. It was a wake-up call, proving that even after decades of GRB research, the universe can still deliver surprises that rewrite the playbook. And with next-generation instruments like the Vera Rubin Observatory coming online, we might soon find out whether this was a once-in-an-era fluke, or just the first of many cosmic light shows we're finally equipped to see. Here's a common cosmic misconception that gamma rays from these bursts race ahead of other light, arriving at Earth first because they're somehow faster. But the truth is far stranger and reveals how the universe plays tricks with perception. Every gamma-ray burst is actually a multi-wavelength fireworks show, emitting radiation across the entire electromagnetic spectrum, from deadly gamma rays down to visible light, all at the exact same moment. The key difference, not their speed, but how they interact with the obstacles in their path. All light, whether it's gamma rays, X-rays, or visible wavelengths, travels at the universal speed limit, 299,792,458 meters per second in a vacuum. That's non-negotiable, but when this radiation plows through the sparse gas between galaxies, lower energy photons like visible light get subtly delayed. Why? Because they're more likely to interact with electrons in interstellar and intergalactic space, scattering slightly off course like commuters navigating a crowded sidewalk. Gamma rays, being far more energetic, bulldoze through almost unimpeded. This creates an illusion of staggered arrival times. When telescopes detect a GRB, the gamma rays show up first, followed by X-rays, then visible light sometimes minutes or hours later. It's not because they left the burst at different times or moved at different speeds. Imagine two runners on identical treadmills, one sprinting through open air, the other wading through waist-high water. Both are equally fast in principle, but their environments slow them down differently. That's exactly what happens across cosmic distances, where even near-perfect vacuum contains enough atoms to subtly hinder certain wavelengths. This principle also explains why GRB afterglows shift color over time. The initial gamma-ray pulse is often followed by a blazing X-ray afterglow, which then fades through ultraviolet and into visible light, like a cosmic ember cooling from white-hot to red. By tracking these changes, astronomers can reconstruct the burst's environment. A rapid fade might mean the jet plowed into sparse interstellar space, while a prolonged afterglow suggests it slammed into dense gas clouds, clues about the stellar neighborhood where the explosion occurred. The myth of faster-than-light gamma rays likely stems from their reputation as the universe's most energetic radiation, but energy and speed aren't the same thing. Gamma rays pack a punch because each photon carries more energy, not because it moves quicker. In fact, if you could witness a GRB up close from a very safe distance, you'd see all wavelengths burst into existence simultaneously, a split-second flash containing everything from invisible gamma rays to a blinding visible light show. It's only after traversing millions or billions of light years that the universe's subtle filtering effects become apparent. This realization reshapes how we interpret GRB data. When telescopes detect time gaps between wavelengths, it's not a fluke. It's a breadcrumb trail revealing the composition and density of the space between galaxies. Some bursts even show multiple echoes as their light reflects off intervening dust clouds, creating a sort of cosmic sonar map. Far from being a confusing artifact, these delays are gold mines of information, helping astronomers piece together the large-scale structure of the universe, one scattered photon at a time. Next time you hear about a gamma-ray burst, remember what we see isn't just about the explosion itself. It's also about the epic journey its light took to reach us and how the universe leaves its fingerprints on every wavelength along the way. The delays aren't bugs in the data, they're features, whispering secrets about everything the light passed through on its billion-year voyage to Earth. Some of the universe's most dazzling light shows aren't powered by nuclear fusion, they're fueled by pure atomic alchemy. When two neutron stars finally spiral together after a gravitational dance lasting millions of years, their collision does more than create a gamma-ray burst. It triggers a kilonova, an explosion so luminous it momentarily rivals small galaxies. Unlike conventional supernova that shine from heat, these events glow with the eerie light of radioactive decay, as freshly forged heavy elements like gold and platinum spray outward at relativistic speeds. The physics behind this phenomenon reads like a cosmic recipe for destruction and creation, as neutron stars, each cramming a sun's worth of mass into a city-sized sphere, approach their final moments. Tidal forces begin shredding their ultra-dense surfaces. When they finally merge, the impact releases a shockwave so powerful it temporarily overcomes neutron degeneracy pressure, the quantum force that normally keeps these stellar corpses from collapsing further. For a brief instant, the combined mass forms a hypermassive neutron star before likely collapsing into a black hole, but not before ejecting neutron-rich material in a swirling, expanding torus. This ejected matter becomes the kilonova's fuel through a process called rapid neutron capture. Free neutrons bombard atomic nuclei at incredible rates, so fast that nuclei can't stabilize between absorptions. A single iron atom might gulp 50 neutrons in milliseconds before some bait to decay into protons, transforming into exotic heavy isotopes of gold, platinum, or uranium. All these freshly minted unstable elements immediately begin decaying, their nuclear furnaces heating the expanding debris cloud to hundreds of thousands of degrees. The result, a rapidly cooling fireball that shifts from blinding blue to deep red over days as different elements decay at varying rates. Astronomers first confirmed this model in 2017 with GW170817. The kilonova's light curve matched simulations perfectly, an initial blue glow from lighter R-process elements like cesium and tellurium, followed by redder emission as heavier elements like lanthanides took over. Spectroscopy later revealed strontium in the ejector, proving neutron star mergers as cosmic crucibles for elements heavier than iron. Considering the event likely produced over 10 Earth masses of gold alone, it's staggering to realize that most precious metals on Earth, from jewelry to electronics, originated in similar cataclysms billions of years ago. What makes kilonovae special isn't just their brightness, which can reach 10,000 times that of a classical nova, but their role as universal element factories. Before their discovery, astronomers debated where exactly the heaviest elements formed. Supernova contribute some, but models showed they couldn't produce enough. Kilonovae solved this by operating like cosmic smelters, efficiently converting neutron-rich material into rare Earth metals and precious elements in seconds. Each merger seeds its galaxy with enough heavy elements to form rocky planets, and perhaps life itself. These events also serve as laboratories for extreme physics. The neutron-rich environment recreates conditions not seen since the universe's first seconds, allowing scientists to test nuclear theories impossible to probe on Earth. Some models suggest certain kilonovae might even produce free neutronium exotic matter composed entirely of neutrons before it decays into more stable forms. Others predict strange quark matter could briefly exist in the merger's aftermath. Every new kilonova detection offers data to refine these wild theories. While kilonovae fade within weeks, their legacy lasts billions of years. The elements they disperse eventually become part of new stars, planets, and possibly even living organisms. In a very real sense, we're all made from the ashes of these cosmic collisions, the ultimate demonstration of how the universe's most violent events give rise to its most beautiful complexities. The next time you see a short gamma ray burst flash across the sky, remember, it's not just an explosion you're witnessing, it's the universe's way of recycling itself into something new. Gamma ray bursts do more than dazzle us with their brilliance. They act as cosmic surveyors, mapping out where and when the universe's most massive stars were born. Because these bursts originate from the deaths of stellar giants, their locations paint a vivid picture of star formation across cosmic history. The farther back we look, the more GRBs we find in small, chaotic galaxies brimming with young, metal-poor stars and environments strikingly different from our mature Milky Way. These bursts are like flashing neon signs in the cosmic darkness, marking nurseries where stars formed at rates hundreds of times faster than today. The connection between GRBs and star formation isn't accidental. Only the most massive stars, those 30 times heavier than our Sun or more, have the potential to collapse into gamma-ray bursts. These behemoths burn through their fuel in just a few million years, exploding as hypernova long before smaller stars like our Sun even settle into maturity. So when we detect a GRB, we're not just seeing a random explosion. We're pinpointing a region where stellar giants recently formed and died in quick succession. The abundance of bursts in a given era thus serves as a direct proxy for how vigorously massive stars were being born at that time. This relationship flips traditional astronomy on its head. Normally, measuring star formation in distant galaxies relies on detecting faint starlight, a challenge when observing the early universe's dim, dusty galaxies. But GRBs cut through the obscuration. Their intense gamma rays pierce through gas and dust that would hide ordinary starlight, while their afterglows provide backlighting to study the chemistry of their host galaxies. Even more remarkably, GRBs are so bright we can spot them in galaxies too faint to detect, otherwise giving us a way to study star formation in the universe's smallest, earliest building blocks. The data reveals a surprising trend. The early universe was a GRB factory. At redshifts above 2, when the cosmos was less than a third of its current age, bursts were perhaps 10 times more common than today. This matches theories that the first generations of stars included far more supermassive varieties, formed in pristine clouds of hydrogen and helium untouched by previous stellar generations. These metal-poor environments favored the birth of unstable giants, stars that lived fast, died young, and left behind brilliant gamma-ray bursts as their tombstones. Some of the most compelling evidence comes from GRB host galaxies themselves. When astronomers finally pinpoint these faint, distant systems, they often find compact, irregular dwarfs, galaxies barely 1% the mass of the Milky Way, yet producing stars at frenzied rates. Their spectra show a striking absence of heavy elements, reinforcing the link between low metallicity and GRB production. This makes sense theoretically. In metal-poor gas, stars form with puffed-up outer layers that rotate faster, preserving the angular momentum needed to power ultra-energetic jets when they collapse. But there's a twist. Not all GRBs follow this rule. A small fraction occur in more metal-rich galaxies, suggesting our understanding isn't complete. Perhaps magnetic fields, binary star interactions, or other factors sometimes override the metallicity effect. These outliers are gold mines for research, hinting at undiscovered pathways to gamma-ray burst formation. By treating GRBs as cosmic census takers, astronomers have reconstructed the universe's star-forming heyday, a period around 10 billion years ago when galaxies churned out stars at peak rates. The decline in GRBs since then mirrors the universe's slowing star formation, as gas supplies dwindled and galaxies grew more sedate. Yet every distant burst remains a time capsule, preserving snapshots of an era when the cosmos was ablaze with the births and deaths of stellar titans, a fireworks show we're only now beginning to decode. Among the most puzzling cosmic messengers are neutrinos, ghostly particles so elusive they can pass through light years of lead without a single interaction. Yet these phantoms of the particle world might hold clues to gamma-ray bursts' most energetic secrets. In a tantalizing twist, the same record-shattering GRB 221009 that dazzled astronomers may have also flung a high-energy neutrino toward Earth, detected by the Ice Cube Observatory buried deep in Antarctic ice. If confirmed, this tentative link would crack open new windows into how GRBs accelerate particles to unimaginable energies. The connection makes theoretical sense. Gamma-ray bursts aren't just luminous, their relativistic jets are natural particle accelerators far more powerful than anything on Earth. As charged particles spiral through intense magnetic fields near the newborn black hole, they gain staggering energy before colliding with photons or other particles. These crashes can produce secondary particles, including neutrinos, neutral, nearly massless entities that escape the chaos unimpeded. Unlike light, which scatters or absorbs, neutrinos travel cosmic distances in a straight line, carrying information about their birthplace's innermost workings. But proving GRB's neutrino factories is fiendishly difficult. Even Ice Cube, a cubic kilometer of ice laced with sensors, catches just a few hundred cosmic neutrinos annually. Most come from random directions, making it hard to pin them to specific sources. When a neutrino arrival coincides with a GRB, as happened with GRB 221009A, the challenge is calculating the odds it's a coincidence rather than a true association. Preliminary analysis suggested just a 1 in 500 chance the alignment was random, intriguing but not definitive. What's at stake goes beyond gamma-ray bursts. For decades, astronomers have hunted the origins of ultra-high-energy cosmic rays, subatomic particles, racing through space at energies 1,000,000 times beyond human-made accelerators. Many suspect GRBs could be these cosmic bullet factories, but cosmic rays' charged nature means their paths twist in magnetic fields, obscuring their birthplaces. Neutrinos, being neutral, would solve this by pointing straight back to their sources like cosmic arrows. A confirmed GRB neutrino link would essentially hand scientists a roadmap to the universe's most powerful particle accelerators. The hurdles are immense. To definitively connect neutrinos to GRBs, detectors may need 10 times ice cube sensitivity, or a once-in-a-century burst even brighter than the BOT. Upgraded detectors like IceCube Gen 2 or future space-based neutrino telescopes could tip the scales. Until then, each candidate neutrino from a GRB serves as both clue and tease, a whisper from the universe's most violent engines, hinting at particle physics beyond our wildest experiments. Every flash in the gamma-ray sky might not just be light announcing stellar death, but the first notes in a far grander symphony of invisible particles we're only beginning to hear. Gamma-ray bursts may light up the distant universe, but if one erupted too close to home, it wouldn't be a spectacle, it would be an existential threat. A strike from a GRB within our own galaxy could unleash havoc on a scale dwarfing any natural disaster Earth has ever seen. The math is terrifying. A burst just 6,000 light-years away, practically next door in cosmic terms, could deliver enough radiation to strip our planet's ozone layer within seconds. Without this protective shield, lethal ultraviolet rays from the sun would bombard the surface, triggering mass extinctions, ecosystem collapse, and a planet-wide crisis resembling nuclear winter. Some scientists even suspect Earth may have already suffered such an attack. 450 million years ago, during the Ordovician period, a sudden extinction wiped out nearly 85% of marine species. While asteroid impacts and volcanism are usual suspects, clues in the fossil record hint at something more exotic. Rock layers from that era show a puzzling spike in mutagenic isotopes, rare elements like iron-60 that typically form in supernova or neutron star collisions. This has led some researchers to propose that a nearby GRB, possibly from a dying hypergiant star or colliding neutron stars, could have bathed Earth in a deadly gamma-ray bath, shredding the ozone layer and exposing life to brutal solar radiation for years. The physics behind this doomsday scenario is chillingly straightforward. Gamma rays themselves wouldn't reach the surface, our atmosphere absorbs them high above. But their energy would trigger a cascade of chemical reactions, breaking apart oxygen and nitrogen molecules to form nitrogen oxides. These compounds act like ozone-eating catalysts, destroying the UV-blocking layer faster than natural processes can rebuild it. Simulations suggest a 10-second burst from 500 parsecs away could deplete 30 to 50% of our ozone, with full recovery taking nearly a decade. An eternity for ecosystems exposed to unfiltered sunlight. But the damage wouldn't stop there. Secondary effects could include acid rain from atmospheric nitrogen fixation, global cooling as nitrogen oxides scatter sunlight, and DNA mutations across exposed species. Phytoplankton, the base of the ocean's food chain, would be especially vulnerable to UV damage, triggering collapses that ripple upward. Land plants might suffer leaf sterilization, while animals would face increased cancer rates and blindness. It's a stark reminder that the universe's most dazzling light shows come with a dark side. Fortunately, the odds are in our favor for now. Surveys of our galactic neighborhood reveal no GRB candidates close enough to pose an immediate threat. The nearest potential progenitor, the Wolf-Rayet star WR104, sits safely 8,000 light-years away, too distant for its inevitable collapse to affect us. Even Eta Carinae, a volatile supergiant primed to explode, is 4 times farther than the danger zone. Statistically, a lethally close GRB strikes Earth only once every few 100 million years, making it a rare but sobering cosmic bullet to dodge. Yet the risk isn't zero. Unlike asteroids, which we could theoretically deflect, a GRB offers no warning or defense. Its light arrives at the same instant as its lethal radiation, giving zero time to react. This invisibility makes GRBs one of the few natural threats we're utterly powerless against, a humbling reminder that despite our technological prowess, we're still at the mercy of the cosmos's whims. But here's the silver lining. While nearby GRBs are devastating, their rarity makes them less pressing than climate change or asteroid impacts. They're a reminder to cherish our planet's fragile equilibrium and perhaps one day become a multi-planet species. After all, if humanity spreads to other star systems, even a galactic gamma-ray burst couldn't erase us entirely. Until then, we can take comfort in the vast emptiness separating us from the universe's most violent engines and keep watching the skies, not just in wonder but with vigilance. Some gamma-ray bursts aren't just powered by gravity, they're turbocharged by magnetic fields of almost incomprehensible strength. Enter the magnetar model, where newborn neutron stars with magnetic fields a quadrillion times stronger than Earth's become cosmic power plants, channeling mind-bending energies into focused jets that we observe as GRBs. To grasp this scale, picture Earth's protective magnetic field gentle enough to guide compass needles at just 0.5 Gauss. Now imagine a stellar corpse with a field hitting 10 to the 15th Gauss, so intense it could erase credit cards from halfway across the solar system. These magnetic monsters form when certain massive stars collapse, their cores preserving and amplifying the parent star's magnetic field like a cosmic dynamo. As the newborn neutron star's interior churns at unimaginable densities, charged particles spiral along field lines, transforming it into an electromagnet of astronomical proportions. The energy stored in these fields is staggering enough to power the sun for billions of years, released in seconds. When such a magnetar forms, its magnetic brakes slow the star's rotation violently, converting rotational energy into a firestorm of gamma rays and particle jets. The magnetar model explains some puzzling GRB traits. Ordinary collapsar jets sometimes struggle to account for the sustained energy output seen in certain long bursts. But a magnetar's fields act like cosmic railguns, continuously accelerating particles even after the initial collapse. This could explain bursts with plateaus in their light curves, periods where emission holds steady before fading, as if a cosmic engine kept running. Some ultra-long GRBs lasting hours might represent magnetars with particularly tenacious magnetic fields, their energy reservoirs draining slowly. What makes these fields so destructive is their organization. Unlike Earth's messy field, a magnetar's lines are thought to be tightly wound near the poles, forming twisted ropes that snap and reconnect, a process called magnetic reconnection. Each snap unleashes pent-up energy like a rubber band breaking, heating plasma to billions of degrees and flinging it outward at relativistic speeds. These magnetic eruptions can outshine the neutron star's thermal emissions, dominating the burst's energy budget. Astronomers suspect magnetar-powered GRBs might leave behind distinct forensic evidence. Their jets could carry unique polarization signatures, patterns in the light's orientation caused by the orderly magnetic acceleration. Future instruments like the Colossus telescope aim to detect these fingerprints, distinguishing magnetar bursts from black hole-powered ones. There's also the curious case of GRB 2011-11-6, a burst whose X-ray afterglow showed bizarre, repeating flares that some theorists attribute to a magnetar's persistent magnetic activity. Yet magnetars aren't invincible. Too much rotational energy loss can cause the star to collapse into a black hole mid-burst, potentially creating hybrid light curves where an initial magnetar-powered phase gives way to a black hole-dominated one. Other models suggest some magnetars might die by fracturing their crusts in starquakes, releasing tsunamis of magnetic energy that could power yet another type of transient cosmic explosion. Earth's humble magnetic field shields us from solar wind, but magnetars rewrite the rules entirely. Their fields are so strong they distort the quantum vacuum, affecting how light propagates near the star. In their presence, empty space itself becomes birefringent, splitting light into two polarized beams like a cosmic crystal. For astrophysicists, these extreme environments are natural laboratories, offering glimpses of physics under conditions no Earth experiment could replicate. Every magnetar-powered GRB is more than an explosion. It's a magnetic masterpiece painted across the cosmos on the largest possible canvas. Long before galaxies filled the cosmos with starlight, the universe was shrouded in a thick fog of neutral hydrogen, a relic from the Big Bang that absorbed ultraviolet radiation like cosmic sunscreen. This primordial mist persisted for hundreds of millions of years until the first generations of stars and galaxies began burning through it in a process called reionization, transforming the universe from opaque to transparent. Gamma-ray bursts from this era serve as celestial flashlights, their afterglows piercing the fading haze to reveal how and when this cosmic transformation unfolded. What makes these ancient bursts so valuable is their ability to backlight the early universe. As a GRB's afterglow travels billions of light years toward us, it passes through clouds of neutral hydrogen that absorb specific ultraviolet wavelengths, creating dark absorption lines in the burst spectrum. The pattern of these lines acts like a chemical barcode. The deeper and wider they are, the more neutral hydrogen the light encountered. By analyzing GRBs from progressively earlier cosmic epochs, astronomers can track how these absorption features weaken over time, marking the gradual clearing of the hydrogen fog. One breakthrough came with GRB 050904, a burst from when the universe was just 900 million years old. Its afterglow spectrum showed nearly complete absorption of ultraviolet light, indicating it had passed through vast reservoirs of neutral hydrogen. Compare that to GRB 130606a, originating 700 million years later, whose spectrum revealed patchy, partially ionized gas. This stark difference captures reionization mid-stride the universe halfway through its transformation from darkness to light. The timing aligns with other cosmic clues. Quasars from similar epochs show shrinking absorption zones around them, bubbles of ionized space carved by their intense radiation. But quasars are rare beasts found only in massive galaxies. GRB, by contrast, occur in galaxies of all sizes, including the small, faint systems likely responsible for most of reionization's heavy lifting. A single GRB afterglow can probe multiple gas clouds along its line of sight, mapping the uneven progress of ionization like a pinprick spotlight sweeping across cosmic history. Perhaps most astonishing is what these bursts reveal about the reionization process itself. Early models suggested a smooth, uniform transition, but GRB data hints at chaos. Some lines of sight show nearly fully ionized paths billions of light years long, while others, even from the same era, remain choked with neutral hydrogen. This patchiness suggests reionization wasn't a tidy global event, but a messy, localized transformation where ionizing radiation leaked through some regions faster than others, like sunlight breaking through morning fog in scattered clearings. The implications stretch beyond cosmic archaeology. By confirming that reionization was largely driven by faint, numerous galaxies rather than a few brilliant quasars, GRBs help solve a long-standing puzzle: how enough ultraviolet photons were produced to ionize the entire cosmos. Their data suggests small galaxies, though individually dim, collectively outshone giants during this era, a testament to how the universe's most transformative work often happens in its humblest corners. Every distant burst that survives from this epoch isn't just a flash in the dark. It's a witness to the moment the universe turned on the lights. most gamma-ray bursts fade predictably, a brilliant flash followed by a gradual dimming. But some refuse to die quietly. Enter the Lazarus bursts, named after the biblical figure resurrected from the dead. These cosmic anomalies suddenly flare back to life hours or even days after their initial explosions. GRB 100814 stands as the prototype, its afterglow mysteriously brightening not once, but twice, first at 9 hours post-burst, then again 2 days later with an energy surge rivaling its original eruption. This wasn't some instrumental glitch. Multiple telescopes confirmed the revival, leaving astronomers scrambling for explanations. The leading theory points to black hole indigestion. When a massive star collapses, most of its material forms an accretion disk that the newborn black hole consumes rapidly, powering the initial gamma-ray jet. But what if some debris takes a scenic route? Imagine a stellar corpse with an especially messy death, where chunks of star stuff spiral inward at different rates. Some might temporarily stall in unstable orbits, creating delayed meals for the black hole. When these stragglers finally plunge in days later, the sudden influx of fresh material could reignite the jet engine, producing secondary flares that defy conventional models. Another possibility involves magnetic turbulence in the accretion disk. As the black hole's gravity shreds the dying star, the resulting disk isn't smooth. It's a churning maelstrom of plasma and magnetic fields. Occasionally, these fields might snap and reconnect in violent episodes, like cosmic short circuits dumping stored energy into renewed particle acceleration. This could explain flares with quasi-periodic brightness oscillations, flickers suggesting some underlying rhythmic process, perhaps the wobbling of a warped disk or precessing jets. The most exotic explanation invokes a magnetar powering through an identity crisis. If the collapsing star forms a highly magnetized neutron star instead of a black hole, its magnetic field might initially channel energy into relativistic jets. But as the magnetar's rotation slows, it could collapse into a black hole days later, triggering a second explosion when the remaining material suddenly loses its magnetic support and free falls into the newborn singularity. This two-stage collapse would imprint as distinct energy releases separated by an unusual gap. Lazarus bursts aren't just cosmic oddities, they're stress tests for astrophysical models. Their late flares challenge assumptions about how quickly black holes quench their jets, hinting that accretion disks might remain active far longer than simulations predict. Some researchers even speculate these events could produce distinct gravitational wave signatures, should future detectors become sensitive enough to catch the whispers of delayed matter impacts. Every resurrected GRB carries a message that stellar deaths aren't always clean, one and done affairs. Sometimes stars die in fits and starts, their final moments drawn out in violent spasms that rewrite the rules of cosmic catastrophes. As astronomers catch more of these rebellious bursts, each new flare peels back another layer of mystery about how black holes and neutron stars transition from birth to maturity. The universe, it seems, enjoys keeping even its most violent phenomena unpredictable until the very end. We might not be alone in the universe, but gamma-ray bursts could explain why it feels that way. This cosmic Grim Reaper hypothesis suggests these explosions don't just destroy stars, they might routinely sterilize entire galaxies, resetting the clock for life over and over. Studies crunch the numbers and the results are chilling. Up to 90% of the universe's habitable real estate could be bathed in lethal GRB radiation, often enough to prevent complex life from gaining a foothold. Earth, it seems, won the cosmic lottery by being in one of the rare quiet neighborhoods. The logic is disturbingly simple. For life to evolve beyond microbes, a planet needs billions of years of stable conditions, but GRBs strike with the frequency of celestial gunfire. In active star-forming regions where massive stars are born and die rapidly, bursts may occur every few million years. Each eruption floods nearby systems with enough high-energy radiation to strip atmospheres, mutate DNA, and trigger mass extinctions. Even if life emerges, it could be stuck in a perpetual cycle of annihilation and rebirth, never reaching intelligence before the next gamma-ray hammer falls. Our own galactic backyard reveals how precarious this balance is. The Milky Way's GRB risk isn't uniform, it's concentrated in the star-rich central regions and spiral arms. Earth orbits in a relatively sparse suburban zone, 27,000 light-years from the bustling core. Cosmically speaking, we're tucked away in a quiet cul-de-sac, shielded not just by location but by timing. The era when our solar system formed, 5 billion years after the Big Bang, coincided with declining star formation rates, meaning fewer potential GRB progenitors nearby. Arrived too early when the universe was GRB dense, or settled too close to a stellar metropolis, and your planet's story might end before multicellular life even gets started. Astrobiologists modeling this phenomenon found sobering patterns. Elliptical galaxies, despite having abundant old stars, may be GRB dead zones. Their star formation fizzled out long ago, leaving few massive stars to explode. But young, metal-poor dwarf galaxies, they're GRB factories, likely bathing their planets in sterilizing radiation every few 100 million years. Even within spiral galaxies like ours, the galactic habitable zone could be razor-thin, a narrow band far enough from the dangerous core yet close enough to have adequate heavy elements for rocky planets. This puts a brutal spin on the Fermi paradox. If GRBs routinely reset life's evolutionary clock, the universe might be teeming with microbes but devoid of civilizations. Earth's 4 billion-year march from amino acids to astronomers could be vanishingly rare, not because life is improbable, but because the cosmos keeps flipping the game board before intelligence can emerge. It's a humbling thought. Our existence might depend as much on cosmic geography as biology, a fragile spark sheltered by sheer luck in a universe that's mostly hostile to stories like ours. Yet there's a tantalizing counterpoint. Some calculations suggest GRBs might paradoxically aid life's spread. Just as forest fires clear space for new growth, periodic sterilizations could prevent any single species from dominating a galaxy, allowing fresh evolutionary experiments each time. And extremophiles, Earth's radiation-resistant bacteria, hint that life might find ways to endure even these apocalyptic blasts, perhaps sheltering deep underground or underwater. The truth likely lies between these extremes. GRBs don't make life impossible, but they might ruthlessly narrow the window for intelligence to evolve, turning the cosmos into a labyrinth where only a lucky few ever find the exit. Astronomers have a cosmic mystery on their hands. A glaring shortage of gamma-ray bursts from the universe's earliest epochs. Based on star formation rates in the primordial cosmos, we should be drowning in distant GRBs. Yet telescopes spot far fewer than predicted from redshifts beyond 4, when the universe was less than 2 billion years old. This missing GRB problem has become one of modern astrophysics' most intriguing puzzles, with theories ranging from the nature of the first stars to fundamental gaps in our detection capabilities. One compelling explanation points to the unique chemistry of the early universe. The first generations of stars formed from pristine hydrogen and helium, elements too simple to efficiently cool collapsing gas clouds. This likely produced monster stars hundreds of times more massive than our Sun, blazing at temperatures over 100,000 degrees. When these behemoths died, they may have collapsed directly into black holes without the messy accretion disks needed to power GRB jets. Alternatively, their low metal composition could have prevented the dense stellar winds that help spin up GRB progenitors in modern stars. Essentially, the earliest stellar deaths might have been more fizzle than sizzle, producing black holes too quietly to trigger the relativistic jets we detect as bursts. Another possibility is that we're simply missing the most distant GRBs because they're hiding in plain sight. The highest redshift bursts have their light stretched so dramatically that much of it shifts into the infrared, a spectrum where our telescopes have limited sensitivity. NASA's SWIFT satellite, which has detected most known GRBs, is optimized for gamma and X-rays, not the far redshifted afterglows. Even when we do spot these ancient flashes, their faint host galaxies often evade detection, leaving us blind to whether they originated in proto-galaxies too small and dim to see. There's also the time dilation effect to consider. A 1-second burst emitted 13 billion years ago would appear stretched to over 9 seconds by the universe's expansion, blurring the line between short and long GRBs. Combined with lower energy photons shifting out of detectable ranges, this could mean some ultra-distant bursts are being misclassified or overlooked entirely. Future observatories like the James Webb Space Telescope, with its unparalleled infrared capabilities, may finally pull these shy cosmic fireballs out of hiding. But perhaps the most tantalizing theory suggests we're witnessing the actual dawn of GRB production. The missing bursts might not be missing at all. They could mark the era before the first stars developed the right conditions to create these explosions. GRBs require not just massive stars, but rapidly rotating ones with strong magnetic fields. If the universe needed time to learn how to spin stars fast enough through mergers or accretion, the truly first-generation stars might have been GRB duds. This would make every burst we do detect from these epochs a precious rarity, the first violins in a cosmic orchestra that hadn't yet figured out its crescendo. Each undetected GRB from the cosmic dawn represents a lost chapter in the universe's biography. Whether they're absent due to stellar physics, observational limits, or cosmic evolution's timing, solving this mystery will rewrite our understanding of how the first stars lived, died, and shaped everything that followed. The missing bursts aren't just gaps in our data, they're silent witnesses to the universe's awkward, explosive adolescence. Cosmic distances can be tricky to measure, but astronomers have long relied on certain celestial objects as standard candles, reference points with known brightness that help map the universe's expansion. Supernova, especially type Ia, have been the gold standard for decades, their consistent peak luminosity making them ideal cosmic yardsticks. But what if gamma-ray bursts could serve the same purpose? Their mind-bending brilliance makes them visible across billions of light-years, potentially offering a way to probe even deeper into the cosmos than supernova can. The catch: GRBs are anything but consistent. The idea isn't far-fetched. Like supernova, gamma-ray bursts have detectable afterglows, and their light curves, how their brightness changes over time, follow patterns that might correlate with intrinsic luminosity. The challenge lies in their wild diversity. A typical type Ia supernova releases energy within a narrow range, but GRBs vary by factors of millions. One burst might emit 1,000 times more energy than another, even if they originate at similar distances. This makes it nearly impossible to judge a GRB's true brightness based solely on how it appears from Earth. Yet researchers have made surprising progress by focusing on subtle relationships between burst properties. The Amati relation, for instance, links a GRB's peak energy to its total radiated energy, a pattern that holds across many bursts, suggesting an underlying physical consistency. Another clue comes from the time-luminosity correlation, where brighter bursts tend to have smoother light curves with fewer fluctuations. These patterns aren't perfect, but they've allowed astronomers to use GRBs as rough distance indicators, especially for redshifts beyond where supernova fade into obscurity. The debate hinges on whether these correlations are universal or just statistical quirks. Critics point out that GRB emission depends heavily on jet geometry, whether we're seeing the beam head-on or at an angle, which could skew measurements. Supporters counter that by analyzing large samples and correcting for biases, GRBs could complement supernova, extending the cosmic distance ladder to eras when the universe was less than 1 billion years old. Already, bursts like GRB 080319 have helped constrain dark energy models, their extreme distances providing data points no supernova could match. The stakes are high. If refined, GRB standard candles could map the universe's expansion during the poorly understood dark ages before galaxies fully formed. They might even reveal whether dark energy's strength has changed over cosmic time, a question central to modern cosmology. For now, GRBs remain a tantalizing but unproven tool, their potential weighed against their unpredictability. But in a field where every new burst can rewrite the rules, today's challenge might become tomorrow's breakthrough. The universe's brightest explosions could yet become its most precise measuring sticks. For decades, astronomers neatly categorized cosmic explosions into distinct bins: supernova over here, gamma-ray bursts over there. Then came 1998, when a peculiar event in the galaxy ISO 184G82 shattered those clean divisions. Supernova 1998 BW wasn't just another stellar death throes, it was a cosmic chameleon, blurring the line between supernova and GRBs with shocking elegance. This wasn't merely a supernova with a gamma-ray chaser. It represented something entirely new, a hybrid eruption where the energies and mechanisms of both phenomena collided. What made this event extraordinary was its duality. On one hand, 1998 BW displayed classic supernova traits, an expanding shell of debris brightening over weeks as radioactive nickel decayed. But hidden in its light curve were fingerprints of something far more violent. The supernova's ejector raced outward at 30,000 kilometers per second, 3 times faster than a typical supernova, carrying enough kinetic energy to power 100 ordinary stellar explosions. Then came the smoking gun. Satellite data revealed that just before the supernova's optical brightening, a faint gamma-ray burst, GRB 980425, had erupted from the same spot. The two events were undeniably linked, a first in observational astronomy. This hybrid wasn't a fluke but a missing link. Traditional supernova occur when massive stars collapse, their outer layers rebounding off the dense core in a shockwave. Classic long GRBs, meanwhile, arise when collapsing stars form ultra-relativistic jets. SN 1998 BW and its kin occupy a middle ground, explosions energetic enough to produce weak jets, but not sufficiently focused to create a full-blown GRB detectable across the universe. Dubbed hypernova, these events pack 10 times more energy than standard supernova, often leaving behind black holes rather than neutron stars. Their existence suggests a continuum of stellar deaths, where the difference between a GRB and a supernova boils down to jet strength and viewing angle. The implications rewrote textbooks. If weak GRBs could accompany supernova, then perhaps every massive star's collapse produces some gamma-ray emission. It's just usually too faint or misaligned to detect. This also meant that local GRB rates might be higher than thought, with many failed jets hidden inside seemingly normal supernova. The discovery even solved a puzzle: why some supernova, like 2003 DH, were absurdly bright. They weren't ordinary explosions, they were GRB supernova hybrids viewed slightly off-axis. Their energy spread across wider angles rather than concentrated in a narrow beam. Modern surveys have since spotted dozens of these transitional objects, each revealing new facets of stellar demise. Some, like SN 2006-J, showed X-ray emission lasting weeks, evidence of persistent central engines akin to GRBs. Others displayed chemical signatures proving their progenitor stars had shed their hydrogen envelopes before collapsing, a prerequisite for jet formation. Together, they paint a picture where the line between supernova and GRBs isn't just blurred, it's a spectrum with stellar mass, rotation, and magnetic fields determining where an explosion lands on the scale from ordinary to extraordinary. For astronomers, these hybrids are more than cosmic oddities, they're Rosetta Stones for decoding how stars die. Every new example helps refine models of jet formation, showing under what conditions a collapsing star opts for a splash versus a spray. And with upcoming telescopes like the Vera Rubin Observatory set to uncover thousands more, we're on the verge of mapping this continuum in full, revealing the hidden threads that tie the universe's most violent explosions together into a single, spectacular tapestry of stellar destruction. Before 1997, gamma-ray bursts were cosmic phantoms, brilliant flashes that vanished without a trace. Then came the revolution. That February, the Bepo-SAX satellite did something unprecedented. It pinpointed the X-ray afterglow of GRB 970228, a faint but lingering glow that allowed astronomers to finally chase these explosions to their source. Within hours, telescopes swiveled toward the coordinates, capturing the first ever visible light from a GRB and uncovering its host galaxy a staggering 6 billion light-years away. Overnight, gamma-ray bursts went from enigmas to measurable phenomena, their afterglows acting as cosmic breadcrumbs leading back to their origins. This breakthrough opened a golden age for GRB science. Suddenly, astronomers weren't just detecting bursts, they were dissecting them. Afterglows revealed that GRBs aren't instant disappearances but protracted events, emitting X-rays, ultraviolet, visible light, and even radio waves for days or weeks post-explosion. Each wavelength carried unique clues. X-rays traced the relativistic jet's inner workings, optical light unveiled the host galaxy's chemistry, and radio emissions mapped the explosion's shock waves plowing through interstellar gas. Spectroscopy of these afterglows became the ultimate tool for measuring cosmic distances. By analyzing how hydrogen absorption lines shifted toward redder wavelengths, a phenomenon called redshift, scientists could calculate exactly how far the light had traveled, turning bursts into yardsticks for the universe's expansion. The real game-changer was how afterglows exposed GRB environments. In 2003, GRB 030329's afterglow displayed ion emission lines, proof the burst had erupted near a dense metal-rich cloud, likely sculpted by its progenitor star's winds. Other afterglows, like GRB 060218, showed smooth light curves suggesting a clean blast wave expanding into uniform space, while jagged declines hinted at clumpy interstellar material. These details painted vivid portraits of stellar nurseries where GRBs are born, revealing that these explosions prefer chaotic, gas-choked regions where massive stars live fast and die young. Perhaps the most startling afterglow discovery was their role in catching cosmic fugitives, GRBs that seemed to come from nowhere. Before afterglow studies, about 30% of bursts appeared hostless, with no visible galaxy at their location. But with sharper imaging, astronomers realized these weren't loners. Their host galaxies were simply too faint for early telescopes. The afterglow of GRB 050824, for instance, led to a dwarf galaxy 10 times dimmer than the Milky Way, proving GRBs often originate in humble, star-forming dwarfs overlooked by traditional surveys. Today, afterglow observations are a well-oiled machine. When a GRB triggers, satellites like Swift, alerts blast out within seconds, directing robotic telescopes worldwide to capture the fading light. These coordinated efforts have bagged over 1,000 afterglows, building a catalog that spans the cosmos from nearby bursts to explosions barely 500 million years after the Big Bang. Each afterglow is a time capsule carrying fingerprints of the universe's chemical evolution, the growth of galaxies, and the extreme physics governing stellar deaths. What began as a faint X-ray echo in 1997 has become astronomy's most versatile tool for probing the universe's most violent moments and the lasting marks they leave behind. Most gamma-ray bursts announce themselves with a flashy afterglow, a lingering glow across multiple wavelengths that astronomers can study for days, but some are cosmic introverts, vanishing almost as quickly as they appear. These are the dark GRBs, explosions whose afterglows are mysteriously faint or completely absent in visible light. leaving scientists to chase shadows across the electromagnetic spectrum. GRB 050359 set the template, a powerful burst detected by Swift in 2005, with a gamma-ray pulse so bright it temporarily blinded satellites. Yet when telescopes swung toward its location, they found nothing, no optical afterglow, no ultraviolet signature, just eerie silence where there should have been fireworks. The leading theory points to cosmic dust as the culprit. Picture a GRB erupting in a dense stellar nursery shrouded in soot-like carbon grains, the same material that blackens interstellar space in our own galaxy. As the burst's afterglow radiation plows through these dust clouds, visible light gets absorbed and re-radiated as infrared heat, effectively turning a brilliant flash into a smothered ember. Supporting this, some dark GRBs like 050359 eventually revealed weak infrared afterglows with the Spitzer Space Telescope, their light literally dusted into longer wavelengths. But dust isn't the only suspect. Another faction of dark bursts shows equally feeble emissions across all wavelengths, suggesting their jets might be low-energy duds GRBs that barely muster the strength to power conventional afterglows. These could represent off-axis events where Earth lies just outside the jet's narrow cone, catching only sidelong radiation. Alternatively, they might signal failed central engines, black holes that formed too quickly, or neutron stars whose magnetic fields fizzled before sustaining robust jets. The distinction matters because it reveals how often the universe attempts GRBs that fizzle versus those that succeed spectacularly. NASA's Swift satellite has become the premier dark GRB hunter, its rapid slewing ability allowing it to catch these elusive bursts in the act. Since its 2004 launch, Swift has pinpointed dozens of dark GRBs by their lingering X-ray afterglows, which penetrate dust more effectively than visible light. Each discovery tightens the noose around the mystery. Some cases, like GRB 120624b, turned out to be normal bursts hiding behind thick dust lanes in their host galaxies. Others, like GRB 110709b, remain stubbornly dark even in X-rays, hinting at deeper enigmas in jet physics or progenitor stars. The implications stretch beyond classification. If dark GRBs are preferentially found in dusty environments, they could trace obscured star formation, the hidden stellar factories too choked with debris for traditional telescopes to spot. Their host galaxies, when finally identified, often prove to be extreme starbursts, churning out stars at rates that leave Milky Way-like galaxies in the dust. This makes dark bursts potential signposts for the universe's most vigorous and ordinarily invisible stellar nurseries, yet the puzzle isn't fully solved. Upcoming instruments like the Vera Rubin Observatory promise to catch more dark GRBs by scanning vast swaths of sky nightly, while James Webb's infrared eyes can pierce the dust veils that obscure their afterglows. Every dark burst that steps into the light brings us closer to understanding whether these are cosmic accidents or a hidden population rewriting the rules of stellar death. The universe, it seems, still holds some cards close to its chest. Gravity doesn't just bend the paths of planets, it can twist light itself into cosmic magnifying glasses, revealing details about gamma-ray bursts we'd otherwise never see. This phenomenon, called gravitational lensing, occurs when a massive object like a galaxy or black hole warps space-time so severely that it distorts and amplifies light from objects behind it. For GRB, this cosmic quirk offers a rare opportunity. Lensed bursts like GRB 950830 appear brighter and sometimes even multiplied, as if the universe itself is handing astronomers a zoomed-in view of these distant explosions. The mechanics are straight out of Einstein's playbook. When a GRB's light passes near a massive lensing object, space-time curvature splits the beam like a prism, creating multiple images or stretched-out versions of the same burst. GRB 950830, for instance, showed an unusual double peak in its light curve, a potential sign its light took two slightly different paths around an intervening galaxy, arriving at Earth milliseconds apart. These delayed echoes aren't just curiosities, they're gold mines of data. By measuring time delays between lensed images, astronomers can triangulate the lensing galaxy's mass distribution, probing dark matter's invisible scaffolding. But the real magic happens when lensing magnifies ultra-distant bursts. Normally, GRBs from the universe's first billion years are too faint for detailed study. A lucky lensing alignment, however, can amplify their light tenfold or more, exposing spectral details that would otherwise vanish into noise. Imagine scrutinizing a GRB from 12 billion years ago with the clarity of one just 6 billion light-years distant. It's like getting a free upgrade on astronomy's time machine. Already, candidates like GRB 2005036 hint at this potential. Their afterglows suspiciously bright for their redshift. Lensed GRBs also serve as natural laboratories for fundamental physics. The precise timing of delayed images can test alternative theories of gravity. Subtle deviations from Einstein's predictions might emerge over cosmic distances. Even more compelling is their potential to measure the universe's expansion rate independently of traditional methods. Because lensing delays depend on the cosmic distance ladder, comparing them to supernova-derived values could resolve the simmering Hubble tension, where different techniques yield conflicting expansion rates. A single, fortuitously lensed GRB might tip the scales in this debate. The hunt for these cosmic mirages is accelerating. Next-generation telescopes like Euclid and the Vera Rubin Observatory will map millions of galaxies ideal for lensing GRBs, while rapid response networks ensure we catch the fleeting afterglows. Every lensed burst is more than a pretty illusion. It's a chance to peel back layers of cosmic history, probe invisible matter, and test the very laws shaping our universe. In a field where luck plays as much role as skill, gravitational lensing offers something priceless, a way to let the universe do the heavy lifting, bringing the farthest reaches of space and time within our grasp. Gamma-ray bursts unleash unfathomable energies, yet they curiously obey an invisible ceiling, a cosmic speed limit that caps their output around 10 to the 54 ergs. To grasp that scale, picture our sun's entire 10 billion-year energy budget spent in 10 seconds. Yet despite this mind-bending power, GRBs never seem to surpass this threshold, creating what physicists call the Goldilocks puzzle. Why aren't they hotter, brighter, more extreme? The answer might lie in a delicate balance between the raw fury of collapsing stars and the universe's fundamental limits. One compelling explanation points to jet stability. GRB jets are narrow, ultra-relativistic beams, cosmic fire hoses channeled by magnetic fields, but push the energy too high, and these jets could destabilize, their structure fragmenting like an overpressurized hose. Simulations show that beyond 10 to the 54 ergs, the jets risk developing kink instabilities, where magnetic field lines twist and snap, dissipating energy sideways rather than focusing it into a tight beam. This loss of coherence might explain the ceiling. Bursts that try to go bigger end up wasting energy in chaotic turbulence rather than the lethal precision we observe. Then there's the black hole itself, the engine powering this mayhem. According to general relativity, a spinning black hole can convert up to 29% of its mass into energy via the Penrose process. For a typical GRB progenitor star of 20 solar masses, that theoretically permits energy outputs up to 10 to the 55 ergs, yet we rarely see bursts approach even half that. The bottleneck might lie in how efficiently the collapsing star can feed its central black hole. If material falls in too slowly or gets choked by magnetic pressure, the black hole starves before tapping its full potential. But perhaps the most intriguing constraint comes from the progenitor stars themselves. the heaviest stars' potential GRB factories face a paradoxical limit. Stars above 130 solar masses are thought to collapse directly into black holes via pair instability supernova, skipping the accretion disk phase needed for GRB jets. Meanwhile, stars between 25 and 130 solar masses might end their lives as pulsational pair instability supernova, shedding their outer layers in violent spasms before finally collapsing, disrupting the clean, rapid infall required to power a burst. This stellar forbidden zone could naturally cap GRB energies by limiting the mass available for jet formation. Even the universe's expansion might play a role. At redshifts beyond 3, time dilation stretches GRB durations, making their energy release appear more gradual. This could mask ultra-powerful bursts that spread their energy over longer intervals, tricking our instruments into underestimating their true might. Future observatories capable of detecting higher energy photons or neutrinos might reveal whether the Goldilocks ceiling is real or just an observational illusion. The energy puzzle isn't just academic. Understanding these limits helps astronomers distinguish ordinary bursts from exotic outliers like GRB 221009A, which flirted with theoretical maximums. It also guides searches for hypothetical hyperbursts from primordial black holes or other exotic phenomena. Every gamma-ray burst is a cosmic lab experiment, testing the extremes of physics under conditions we can't replicate on Earth. Their self-imposed limits aren't failures, they're clues, pointing toward the delicate balance that governs even the universe's most violent explosions. Gamma-ray bursts usually announce themselves with a fireworks show, first an intense pulse of gamma rays, then a fading afterglow across the electromagnetic spectrum. But what happens when we spot the glow without the initial flash? Enter the mystery of orphan afterglows, cosmic embers hinting at bursts that fired their jets away from Earth, leaving behind only faint echoes of their fury. These elusive events, like PTF-11, a GG discovered in 2011, challenge everything we thought we knew about GRB rates and jet structures, suggesting the universe might be harboring far more of these explosions than our telescopes have caught. PTF-11, a GG, was no ordinary afterglow. Found by the Palomar Transient Factory Survey, it flared in visible light with the same characteristic fade as a classic GRB afterglow, but no gamma-ray satellite had detected a matching burst. At first glance, it behaved like a supernova, but its light curve declined too rapidly, and its spectrum lacked the telltale hydrogen signatures of stellar explosions. The smoking gun came with radio observations. The afterglow's emission displayed the same broadband synchrotron radiation typical of relativistic jets, just without the gamma-ray fanfare. The conclusion was inevitable. Earth had witnessed the sidelong view of a GRB. Its deadly beam pointed somewhere else in the cosmos, while we caught only the faint spillover. These orphans are more than just cosmic curiosities. They're critical for solving the hidden GRB problem. Current estimates suggest that for every gamma-ray burst we detect, there could be hundreds more with misaligned jets, their gamma rays never reaching our instruments. The narrowness of GRB jets, typically just a few degrees wide, means most point harmlessly into the void, betraying their existence only through these chance afterglow sightings. Surveys like the Zwicky Transient Facility now scan the skies nightly for these lonely afterglows, piecing together a truer census of stellar cataclysms. The implications ripple through astrophysics. If orphan afterglows are as common as some models predict, the true GRB rate could dwarf previous estimates, forcing us to rethink how often massive stars die in these hyper-energetic events. It also suggests that what we call a gamma-ray burst might be just the tip of the iceberg, the small fraction of jets that happen to align with our line of sight. Even more intriguing, some orphans might represent entirely new classes of transients, failed jets that lack the punch to produce detectable gamma rays, or hybrid explosions straddling the line between GRBs and supernova. Every confirmed orphan afterglow is a Rosetta Stone for jet physics. By comparing their properties to classical GRBs, astronomers can test theories about jet composition, collimation, and energy distribution. PTF-11, a GG's radio emission, for instance, revealed that even off-axis jets maintain remarkable coherence as they plow through interstellar space, a clue that magnetic fields play a bigger role in stabilizing these outflows than previously thought. Other orphans like CTS 140522+6125 showed unexpected X-ray flares weeks after discovery, hinting at long-lived central engines that keep flickering long after the main event. The hunt for these cosmic strays is accelerating. Next-generation observatories like the Vera Rubin telescope will scan the entire visible sky every few nights, spotting afterglows too fast fading for current instruments. Combined with rapid radio follow-up and neutrino detectors, we might soon uncover a hidden population of GRBs explosions that once slipped through our nets simply because their brightest light never reached us. In a universe where perspective shapes perception, orphan afterglows remind us that what we see depends entirely on where we stand, and that the cosmos always keeps a few secrets in reserve. Gamma-ray bursts may dominate headlines, but they share the cosmic stage with another fleeting phenomenon: fast radio bursts. These millisecond blips of radio energy pack as much punch as hundreds of millions of suns, yet vanish before you can blink. While both GRBs and FRBs represent the universe's most extreme transients, their origins tell vastly different stories, with one spectacular exception that blurred the lines between these cosmic enigmas. Most fast radio bursts play by different rules than their gamma-ray cousins. Unlike GRBs, which trace back to collapsing stars or neutron star collisions, the majority of FRBs appear to be one-off events originating from unknown sources billions of light-years away. Their brevity is staggering. Some last just a fraction of a millisecond, and they show no afterglows or visible counterparts. This has fueled theories ranging from evaporating black holes to hypothetical cosmic strings, though the leading suspects are now highly magnetized neutron stars. The key distinction lies in their energy distribution. While GRBs flood space with gamma rays and X-rays, FRBs channel their power almost exclusively into radio frequencies, like celestial lighthouses flashing across the electromagnetic spectrum. Then came April 2020, when the universe handed scientists a Rosetta Stone. FRB 200428 wasn't just another mysterious blip. It erupted from SGR 1935+2154, a known magnetar in our own galaxy. For the first time, astronomers caught a fast radio burst with simultaneous X-ray flares, proving at least some FRBs stem from these ultramagnetic stellar corpses. The magnetar's outburst mimicked a scaled-down GRB jet, complete with relativistic particle acceleration, suggesting a shared engine mechanism under extreme conditions. But here's the twist: no gamma rays accompanied this event. Unlike classic GRBs, which require powerful jets punching through stellar material, this FRB seemed to originate from magnetic reconnection near the magnetar's surface, a localized storm rather than a directional fire hose. This exception proves the cosmic rule. While both phenomena involve neutron stars and insane energies, their divergence lies in scope and structure. GRBs are demolition derbies, the explosive deaths of stars or collisions that reshape their surroundings. FRB, by contrast, are more like precision lightning strikes, their energy narrowly focused and often repeating. The magnetar connection hints that some FRBs could be GRBs' quieter siblings, operating at lower energies or different angles. Yet the vast majority of extragalactic FRBs show no GRB counterparts, implying distinct formation pathways. The mystery deepens when comparing their cosmic roles. GRBs act as chemical forges and star formation markers, while FRBs might serve as universal yardsticks. Their radio waves interact with intergalactic electrons, allowing astronomers to measure the universe's missing baryonic matter. Some theories even suggest FRBs could probe the cosmic web's filamentary structure, their signals distorted by the invisible gas between galaxies. GRBs illuminate stellar life cycles. FRBs might map the universe's hidden scaffolding. This cosmic dichotomy showcases astronomy's challenge phenomena that seem similar at first glance often stem from fundamentally different engines. The rare overlaps like magnetar-powered FRBs become treasure troves for physicists, offering glimpses into how matter behaves under conditions impossible to replicate on Earth. As detectors grow more sensitive, we may find other transitional objects that blur these categories further, revealing a spectrum of extreme astrophysical events that defy our neat classifications. For now, each new burst, whether in gamma rays or radio waves, adds another piece to the puzzle of how the universe channels unimaginable energies into fleeting cosmic sparks. Gamma ray bursts don't just push the limits of energy, they might be twisting the very fabric of physics itself. Hidden in the spiral dance of their polarized photons could be clues to a theory that's eluded scientists for a century: quantum gravity. The phenomenon at play is called birefringence, where light's polarization changes as it traverses the universe. But here's the cosmic twist: this isn't ordinary birefringence caused by magnetic fields. Instead, it's a potential fingerprint of spacetime itself behaving differently for light waves of varying polarization, a prediction of some quantum gravity models that envision spacetime as a granular, foamy structure at microscopic scales. GRB 021206 became ground zero for this speculation when analyzers suggested its gamma rays exhibited bizarre polarization shifts. According to certain quantum gravity theories, spacetime's hypothetical granularity might treat left and right-handed polarized light differently, effectively making them travel at slightly distinct speeds across billions of light years. Over cosmic distances, this minute discrepancy could accumulate, rotating the light's polarization plane by detectable degrees, a phenomenon dubbed vacuum birefringence. If real, it would mean that the void of space isn't truly empty but seething with quantum fluctuations that leave subtle marks on passing light. Critics were quick to question the GRB 021206 findings. Polarization measurements in gamma rays are notoriously tricky, with instrumental effects easily mimicking exotic physics. Later observations of other bursts failed to consistently replicate the signal, casting doubt on whether the detection was a fluke or a groundbreaking revelation. Yet the tantalizing possibility remains. If future GRBs with superior instrumentation were to confirm vacuum birefringence, it would offer the first observational hook for quantum gravity, a field currently trapped in mathematical abstraction. The implications would rewrite textbooks. Most quantum gravity frameworks, from string theory to loop quantum gravity, predict some form of spacetime granularity, but each variant leaves different imprints on light. Detecting how GRB photons polarize could act as a cosmic sorting hat, distinguishing which theories align with reality. For instance, some models suggest the polarization rotation should increase with photon energy, while others predict dependency on the light's travel distance. A statistically significant sample of polarized bursts could map these patterns, turning the universe into a laboratory for physics beyond Einstein. What makes GRBs ideal for this hunt is their unparalleled luminosity. To spot quantum foam's subtle effects, you need light that's traveled billions of years without scattering, and few cosmic events produce photons as pristine and energetic as GRB jets. Their polarization serves as a cosmic protractor, preserving information about every twist and turn their light experienced en route to Earth. Even a single unambiguous detection could calibrate the grain size of space-time, answering whether the universe's underlying structure is as fine as 10 to the minus 35 meters, the Planck length or coarser. While the chiral puzzle remains unsolved, Next-generation detectors like the proposed COM-pair gamma-ray telescope aim to measure GRB polarization with unprecedented precision. Each new burst is a roll of the quantum dice, potentially carrying the long-sought signature that space-time isn't smooth but built from something far stranger, a trembling web of uncertainty where gravity and quantum mechanics finally shake hands. Until then, GRBs keep whispering encrypted hints, reminding us that the universe's grandest explosions might also be its most precise microscopes. When the blinding fury of a gamma ray burst tears through a galaxy, it doesn't just light up the cosmos, it incinerates everything in its path. One of the most fascinating casualties, interstellar dust, those microscopic grains of carbon and silicates drifting between stars. As the GRB's afterglow radiation floods its surroundings, it vaporizes these tiny particles in a process called dust destruction, leaving behind spectral scars that act like cosmic forensic evidence. These fingerprints don't just reveal what the dust was made of, they expose secrets about the chemical evolution of galaxies in the universe's infancy. The telltale signature appears in the afterglow's light curve. Dust preferentially absorbs shorter, bluer wavelengths, so when a burst light passes through dusty regions, its spectrum reddens like sunlight at sunset. But as the afterglow's intense ultraviolet and X-ray radiation heats the surrounding dust to thousands of degrees, those grains sublimate, transforming directly from solid to gas. This annihilation creates two key spectral shifts: a sudden bluing of the afterglow as dust blockage vanishes, and telltale emission lines from heated silicon and carbon atoms now floating freely where dust once existed. It's as if the GRB lifts a cosmic veil, giving astronomers a momentary peek at the pristine gas behind the dust curtain. GRB 060218 offered a textbook case. Initially, its afterglow showed the classic reddening of dust-obscured light, but within hours, as radiation cooked the surrounding medium, its spectrum shifted blueward while silicon absorption lines surged, proof that silica dust grains were being shattered into their atomic components. Similar bursts near star-forming regions exhibited carbon emission features, evidence of graphite or polycyclic aromatic hydrocarbons getting shredded under the gamma-ray onslaught. These observations confirmed theoretical models predicting that dust destruction happens in stages. First, the icy mantles of grains boil away, then the tougher mineral cores disintegrate. Beyond the pyrotechnics, this process serves as a powerful tool for probing early galaxies. Dust composition evolves over cosmic time. Younger galaxies have simpler, larger grains, while older ones develop complex microstructures from repeated supernova processing. By comparing dust destruction signatures in GRBs across different redshifts, astronomers found that early universe dust was more porous and carbon-rich, a relic of when stars had fewer heavy elements to work with. Some bursts, like GRB 140619a, even revealed dust-free zones stretching hundreds of light-years around their host galaxy's centers, likely cleared by previous generations of stellar explosions. The implications stretch far beyond GRBs. Dust destruction signatures help calibrate how quickly galaxies enrich their environments with heavy elements, a key factor in planet formation. They've also solved puzzles like the missing dust problem in quasars, where models predicted more dust than observed. GRB afterglows now suggest that quasars' intense radiation might be continuously evaporating their surrounding dust reservoirs, creating a dynamic balance between dust creation in stellar winds and destruction by radiation. Every vaporized dust grain tells a story of star deaths that forged its atoms, of turbulent interstellar winds that shaped its structure, and now of a gamma-ray burst that returned it to the cosmic forge. As telescopes grow more sensitive, these fleeting destruction signatures will paint an ever clearer picture of how galaxies transformed primordial hydrogen into the diverse chemistry that makes our existence possible. The universe's most violent explosions, it turns out, are also some of its most meticulous cleaners. gamma-ray bursts don't fade smoothly. They sometimes take a sudden, dramatic nosedive. This plunge, called a jet break, isn't just a quirk of the light curve. It's a Rosetta Stone for decoding the geometry of GRB jets. Picture a lighthouse beam sweeping across the ocean. As long as you're inside the beam's width, the light appears steady. But the moment the beam's edge passes you, the brightness plummets. Jet breaks work the same way. When a GRB's relativistic jet slows enough for its edges to become visible from Earth, the afterglow's decline steepens sharply, betraying the jet's true width. The physics behind this clue is elegant. Initially, the jet's immense speed creates relativistic beaming, an optical illusion where light is concentrated into a narrow cone along the jet's axis. This makes even a several-degree-wide jet appear pencil-thin from our vantage point. But as the jet plows into interstellar material and decelerates, this beaming effect weakens. Once the jet's speed drops below a critical threshold, typically weeks after the burst, its true angular size begins to dominate the light curve. The result: a telltale break where the afterglow's fading rate shifts from gradual to precipitous, often by a factor of 2 or more. One textbook example is GRB 990123. For 18 days, its afterglow faded predictably, then abruptly steepened. Analysis pinned its jet opening angle at 4.7 degrees, narrower than a ping-pong ball held at arm's length. This precision matters because jet angles let astronomers calculate the true energy budget of GRBs. Without accounting for collimation, a burst's isotropic equivalent energy, what we'd infer assuming the emission was spherical, can be wildly exaggerated. GRB 990123's initial flash suggested an impossible 10 to the 54 ergs, but correcting for its 5-degree jet revealed a more plausible 10 to the 51 ergs, still staggering but physically coherent. Jet breaks also expose the diversity of GRB engines. Some bursts, like GRB 030329, show double breaks, hinting at complex jet structures with multiple velocity components. Others defy expectations entirely, like GRB 060614, whose afterglow remained unbroken for months. These outliers suggest certain jets either maintain relativistic speeds unusually long or expand sideways faster than models predict. The most bizarre cases even display late-time flaring post-break, implying the central engine might flicker back to life long after the initial collapse. What makes these breaks invaluable is their role as cosmic protractors. By compiling hundreds of jet angle measurements, astronomers found most long GRBs have opening angles between 2 and 20 degrees narrow enough to explain their extreme luminosities when beamed toward us. Short GRBs, by contrast, tend toward wider angles, reflecting their different neutron star merger origins. This catalog doesn't just refine energy estimates, it reveals how efficiently dying stars channel their fury into focused death beams rather than wasteful spherical explosions. The next time you see a GRB light curve with that characteristic knee-like drop, remember you're witnessing more than a fading afterglow. You're seeing the moment the universe pulls back the curtain, exposing the hidden architecture of nature's most precise particle accelerators. Each break is a geometric confession, revealing secrets about stellar death that no telescope could image directly. In a field where so much remains unseen, jet breaks offer something rare, a way to measure the immeasurable using only the subtle language of fading light. Some gamma-ray bursts seem to come from nowhere, flaring brilliantly in the cosmic darkness with no visible galaxy to call home. These hostless bursts pose a cosmic riddle. How can the universe's most energetic explosions lack something as fundamental as a stellar birthplace? The answer may lie in the shadows of the cosmos, where galaxies too faint or tiny to spot with current telescopes could be hiding in plain sight. Take GRB 050824, a powerful burst that initially appeared to float in empty space. Early follow-up observations found no galaxy at its location down to magnitude 27, more than 100 million times fainter than the dimmest star visible to the naked eye. Yet deeper imaging with the Hubble Space Telescope eventually uncovered a smudge of light, a dwarf galaxy with just 1,000th the Milky Way's mass. This ghostly system, barely distinguishable from background noise, typifies the elusive hosts of many missing GRB. Their diminutive size and low star-forming rates make them incredibly challenging to detect, especially at extreme distances where the universe's expansion stretches their light into near invisibility. But faint galaxies aren't the only explanation. Some hostless bursts might trace their origins to intergalactic vagabonds, massive stars flung from their birth galaxies during violent mergers. When galaxies collide, gravitational chaos can eject stars at speeds exceeding 500 kilometers per second, sending them careening into the void. These rogue stars carry their explosive destinies with them. When they eventually collapse, their GRBs would erupt in the emptiness between galaxies, leaving no host to identify. Supporting this, some field GRBs show absorption lines matching nearby galaxy clusters, suggesting they occurred in intracluster space where ejected stars congregate. The mystery deepens when considering chemical fingerprints. Many hostless bursts exhibit lower metallicity, fewer heavy elements, than bursts anchored to visible galaxies. This aligns with the idea that their progenitors formed in pristine environments, either in underdeveloped dwarf galaxies or from early generation stars ejected before enriching their surroundings with supernova debris. GRB 060505, for instance, showed almost no metals in its afterglow spectrum, hinting at a natal environment resembling the universe's primordial gas clouds. Advancing technology is peeling back the veil. Instruments like the James Webb Space Telescope are now spotting once invisible host galaxies by their infrared glow, proving that many orphan GRBs simply come from systems too dim for older telescopes. Others, however, persist without hosts even under scrutiny, strengthening the case for intergalactic origins. Each discovery refines our cosmic senses, revealing a universe where stellar death isn't confined to galaxies' bustling centers but unfolds in the darkest, most neglected corners of space. What seemed like missing hosts might instead be a lesson in cosmic bias, a reminder that our telescopes have long favored the universe's bright and mighty while overlooking its faint and nomadic inhabitants. As observational limits push deeper, every hostless GRB could become a signpost pointing to populations of galaxies or stars we've yet to properly acknowledge, a hidden tapestry of stellar life and death woven between the galaxies we thought we knew. Gamma-ray bursts may seem like solitary cosmic firestorms, but some might originate from stellar duos locked in a deadly gravitational dance. The binary progenitor theory suggests certain GRBs, especially long-duration ones, could be born from massive Wolf-Rayet stars orbiting compact companions, neutron stars, or black holes that shape the explosion's ferocity. Imagine a stellar heavyweight 20 times more massive than our Sun and stripped of its hydrogen envelope, whirling around a dense partner at dizzying speeds. This intimate partnership doesn't just create spectacular fireworks, it fundamentally alters how the system implodes. When the Wolf-Rayet star exhausts its nuclear fuel, its collapse plays out differently than in single-star scenarios. The companion's gravity injects extra angular momentum into the dying star, spinning its core like a cosmic top. This rotation becomes the secret ingredient for an ultra-powerful burst. As the core collapses into a black hole, the conserved spin energy gets funneled into tighter, more stable jets. Think of how a figure skater's spin accelerates when they pull their arms in. Simulations show these binary systems can produce jets with opening angles under 5 degrees, compared to 10 degrees or more in single-star collapses. The narrower the jet, the more focused its energy, potentially explaining some ultraluminous bursts that defy traditional models. The companion's role doesn't end there. As the primary star collapses, its outer layers might get siphoned onto the neutron star or black hole companion, creating a hyperactive accretion disk. This dinner and a show scenario could prolong the central engine's life, leading to bursts with peculiar plateaus or secondary flares in their light curves. Some astronomers even speculate that the companion itself might eventually plunge into the newborn black hole, triggering a second energy injection, a cosmic encore visible as delayed gamma-ray emission. Observational clues support this stellar tango. The host galaxies of some long GRBs show elevated rates of massive binary systems, while certain afterglows display chemical signatures of transferred material between stars. One smoking gun candidate is GRB 111209A, whose prolonged X-ray afterglow flickered for weeks, behavior easier to explain with a binary engine than a solo collapse. Even the infamous BOAT burst GRB 221009A fits the profile, with energy output and jet structure aligning with Wolf-Rayet black hole binary models. Yet mysteries remain. Binary systems should produce distinctive gravitational wave signals during collapse, but current detectors lack the sensitivity to catch these whispers from distant galaxies. Future observatories like the Einstein telescope might change that, listening for the telltale chirps of black holes forming amid stellar duets. Until then, every peculiar burst, every outlier in energy or structure hints at the invisible partners that might be orchestrating the universe's most violent performances from the shadows. The hunt for gamma-ray bursts is about to leap into hyperspeed, thanks to a new generation of observatories designed to push the limits of cosmic exploration. Leading the charge is the Vera Rubin Observatory, a behemoth under construction in Chile that will scan the entire visible sky every 3 nights with its 3.2 gigapixel camera. This relentless patrol will catch GRBs most telescopes would miss, especially those faint, ultra-distant bursts from the universe's infancy. With the ability to detect objects 10 million times dimmer than the naked eye can see, Rubin could spot GRBs at redshifts beyond 10, when the cosmos was a mere 400 million years old. These flashes would act as time capsules from the epoch of the very first stars, offering a glimpse into stellar populations so ancient they've never been directly observed. But Rubin isn't working alone. The European Space Agency's Athena satellite, launching in the mid-2030s, will bring X-ray vision to the hunt. While Rubin scans invisible light, Athena's advanced X-ray spectrometer will dissect GRB afterglows with unprecedented precision, measuring their chemical fingerprints and the density of intergalactic gas they've traversed. Together, these instruments form a cosmic tag team. Rubin nails down the burst's location within minutes, while Athena's X-ray eyes probe its inner workings. Their combined data could reveal whether the first stars died in spectacular gamma-ray bursts or faded quietly, settling a long-standing debate about the nature of cosmic dawn. The real game-changer lies in their synergy with gravitational wave detectors. When LIGO Next upgrade goes online, its improved sensitivity might catch the ripples from colliding neutron stars simultaneous with Rubin spotting the resulting short GRB. This multi-messenger approach, light, gravitational waves, and possibly even neutrinos, will let scientists reconstruct stellar deaths in 3 dimensions, like cosmic forensic teams piecing together a crime scene from every possible angle. Beyond detection, these tools will test fundamental physics. GRBs at redshifts above 10 could probe quantum gravity effects as their high-energy photons interact with spacetime's hypothetical granular structure over billions of light years. Some theories predict these photons should arrive slightly out of sync depending on their energy, an effect too subtle for current telescopes but potentially within Athena's grasp. Each captured burst becomes a laboratory for extremes we can't replicate on Earth, from the behavior of matter in black hole jets to the validity of Einstein's relativity across cosmic time. The payoff extends beyond astrophysics. By mapping GRB rates across different cosmic eras, these observatories will trace how star formation evolved from the first galaxies to today. Areas with frequent bursts likely hosted prolific generations of massive stars, while GRB deserts might mark regions where stellar birth stalled. This census could reveal why some galaxies like our Milky Way produce few GRBs, while others become relentless burst factories. What makes this new era exhilarating is its potential for complete surprises. Every time humanity has built better observatories, we've uncovered phenomena nobody predicted, from dark energy to magnetars. As Rubin and Athena push into uncharted redshift territory, they might discover entirely new classes of GRBs, perhaps bursts from primordial black holes or exotic supernova powered by dark matter. The universe's final frontier of stellar explosions is finally coming into view, promising revelations about how the first lights in the cosmic darkness lived, died, and paved the way for everything that followed. From the staggering energies of hypernovae to the delicate fingerprints of quantum spacetime, gamma-ray bursts have proven to be more than just cosmic fireworks. They're portals to understanding the universe's most violent and formative moments. These 30 facts paint a breathtaking picture. Bursts erupting when the cosmos was barely 600 million years old, neutron star collisions forging gold by the Earth mass, and orphan afterglows hinting at hidden stellar graveyards between galaxies. Each discovery peels back another layer, revealing how GRBs act as both cosmic signposts, marking where massive stars lived and died, and time capsules preserving snapshots of the universe's chemical and structural evolution across billions of years. What makes distant bursts particularly extraordinary is their duality. They're simultaneously relics of the past and probes of the present. The light from GRB 090423 began its journey when the first galaxies were assembling, carrying with it traces of pristine hydrogen from an era before heavy elements existed. Yet when we analyze its afterglow with modern telescopes, we're also studying how that ancient light interacted with every gas cloud and galactic filament it passed through, effectively using the burst as a backlight to map the universe's growing complexity. It's like finding a fossil that not only shows us an extinct creature, but also reveals the geological layers it traveled through to reach us. These explosions push the boundaries of physics in ways no laboratory ever could. From magnetars with magnetic fields strong enough to distort atoms to jets moving at 99.9% the speed of light, GRBs are natural particle accelerators operating at energies we can scarcely comprehend. They've forced us to reconsider fundamental questions. How do black holes launch and focus such lethal beams? Why do some stellar deaths produce bursts while others fade quietly? And could the elusive Goldilocks limit on GRB energies hint at undiscovered laws governing all relativistic jets? As our detectors grow more sophisticated, from Rubin's all-sky patrols to gravitational wave observatories, the next decade promises even grander revelations. We might finally spot bursts from the universe's absolute dawn, the first generation of stars, or catch a neutrino signal that unlocks the secrets of particle acceleration in jets. Every flash in the gamma-ray sky carries potential discoveries about dark matter, cosmic expansion, or the nature of spacetime itself. The story of gamma-ray bursts is far from complete, and that's what makes them so thrilling. Whether it's the puzzle of missing high-redshift bursts or the enigma of Lazarus-like revivals, these cosmic explosions keep challenging our assumptions. So tell us, which GRB mystery fascinates you most? Is it the potential for quantum gravity signatures hidden in their photons, the way they might have shaped life's evolution across the cosmos? Drop your thoughts below, and don't forget to subscribe for more deep dives into the universe's greatest wonders. The next cosmic revelation could be just a gamma ray